Greetings. One of the things that the Greeks really became good at when they started looking at theoretical mathematics was answering the question, why or how do you solve certain types of problems? And for the Greeks, they would just take off and do all types of interesting mathematics. And for linear equations in one variable, they can all be simplified to the following form. A known number a times an unknown x will be equal to a product b times c. Now, let me explain just for a moment that this is really nothing more than saying a times x is equal to some single number, call it e. Any number e, for the Greeks, because remember they're not going to have zero, can be expressed as a product, even if that product has to be nothing more than 1 times the number itself. For the Greeks, the question was, how can I geometrically prove to myself that I can determine this missing value of x such that for this given value of a, I can produce a given product? Well, let's take a look at what we're going to do. And we see what we're about to do. So what I've done is I've gone into my geometry drawing software and I've provided us with two known segments, the smaller of which is going to be the length of a, our number that is given to us, and then I have the longer, which is going to be the product of b times c. We're going to see that I don't have to actually have a be less than the product of b and c, but for this beginning step, let's go ahead and work it this way. So the first thing the Greeks are going to do then is represent the product of b times c. So let's take a look. And we're back. And what takes place is this idea for the Greeks was the product must be equal to some rectangle. Namely, we're going to have a length b and a width c, or vice versa. But the idea is that this rectangle must be equal to, in area, the length of that segment up there. And I've done some basic math to help us construct this rectangle for that given product. Let's take a look. Some of you may be wondering, is this the only rectangle? And the answer is no. I can actually look at this rectangle in different format. And what I mean by format in this case is form, in the fact that I can create this rectangle to be any rectangle I need. But all of the rectangles will have the identical area of the length of that segment. And we can see this if I now change the length of this segment, my rectangle begins to change shape. So now, once we have the rectangle, the question is, how do we solve the equation ax is equal to this rectangle? Well, our other known needs to be put into the problem. So now let's represent the known value of a. And we're going to do that by extending one side of the rectangle an amount equal to a. So now we have this line that I can extend using Euclid's axioms, and I now have this nice segment that is equal to the given segment a. And we can see that if I go up here and I want to change the length of a, not a problem. It just means I'll change the length of the bit that I constructed. Now then, before we go too far, let's now think about how we're going to find this x. And the Greeks said, okay, not a problem. What we're going to do is go from the end of a, and we're going to hit the rectangle at this vertex and continue on with a ray. And then on this side of the rectangle, we'll continue downward with a line till we find this point, this intersection. Now at this point, it's worthy to note that I need to point out something that you may or may not know. For all rectangles that ever exist, no matter how you draw it, if you put in exactly one diagonal, the area of the triangle above the diagonal, area 1, must be equal to the area below the diagonal, area 2. Any rectangle can be cut into two equal areas by putting in one diagonal. And the Greeks said, okay, let's watch what we can do with this knowledge and this construction. And this is what they did. For a right triangle, you can duplicate it and come up with a rectangle. Now let's look at what this rectangle's telling us. This rectangle has one diagonal put into it. So let's look at this rectangle right here, this little bitty one, where we had A that came out, C went down, and this rectangle's now cut into two congruent right triangles. So I know this triangle on top must be equal to this triangle on the bottom. No problem. Now let's look at this rectangle right here that's provided by this ray that came through on this intersection. We have no idea what this distance right here is, but we know this is B. Well, B times something gives me this rectangle, but since it's a rectangle, I know this right triangle must be equal in area to this right triangle. And with that being the case, now look at the big rectangle. Since everything above this slice must be equal to everything below the slice in terms of areas, and we just basically said this piece is to this one, this little piece is to this little piece, it must mean that this rectangle is equal to this rectangle. Now, don't forget, this rectangle right here is the product of B and C. What is this rectangle? Well, it's A in width and some unknown amount. But what were we trying to solve earlier? A times an unknown amount is equal to the area of a given rectangle. So this little distance right here must be that which we did not know because it wasn't given in the problem. We constructed it. This little piece right here is the missing value x. And let me show this to you in very stark terms. Let's watch what's going to happen. I can put into this problem the inside of this rectangle, which we have said is the product of B and C. And I'm going to put in this rectangle down here, which I'm claiming is A times B. And now let's watch what happens when I measure these two areas. So I'm going to grab both of them, and I am going to measure areas. And I have one area right here. I have another area right here. And what we see is these two areas are exactly the same. And they remain the same for no matter what the construction is. And because I couldn't have made these numbers up on the fly. So what I'm going to do now is I'm going to get rid of these. I don't need them. Now let's watch what happens. If I change the product, no problem. This will just slide back and forth. Notice my construction still works. If I'm over here and I change the length of A, not a problem. It's simply going to slide back and forth, but my construction and the theory behind it still works. Namely that this red rectangle must be equal in area to this off-green rectangle. And because of that, the Greeks satisfied themselves that they had found a solution to AX equals BC. And it is a construction solution. It's not the algebra that we think of, but it's the geometry of why that algebra works. I hope this helps.